Hi again, everyone. Chris Tisdell here again. Thanks for tuning in. In this video, I'm going to continue my live streams of mathematics classes, and we're going to talk about Maclaurin series. I'm going to show you an example, and then I'll show you a nice mathematical application of Maclaurin series. Now, in previous videos, we talked about Maclaurin polynomials, and we computed a few Maclaurin polynomials. The Maclaurin series is the next step, if you like, where instead of a polynomial, we add up an infinite series. So let me show you an example and we can work our way through it. All right, here is the example I'm going to show you. We've got a function, which is the exponential function. We're asked to compute the Maclaurin series for that function. Then we're asked to write down the Maclaurin series for another function, x times e to the x, and finally, it's just out of shot, use differentiation to compute the exact value of this series here. Firstly, why would you want to do that? Well, in a series of videos on infinite series, we know that it's really tricky to actually compute the exact value of a series. That's what we're going to do in this example. So that's a sort of a loose mathematical application. So let's see how it all works. So first off, compute the Maclaurin series for this. Oh, before we get down to that though, let's take a look at Colin Maclaurin. Here he is, Colin Maclaurin, a Scottish mathematician who is attributed with the special series called Maclaurin series. Okay, so let's get to the example. Okay, so a Maclaurin series is of the following form. You have got, I'm just going to write it as T because it's a special form of what's known as a Taylor series. Basically, it just involves the value of the function and its derivatives at 0. So you keep differentiating, you keep evaluating the derivatives at 0. So by the dashes, I mean differentiating with respect to x. And you keep increasing the derivatives, the powers, and the factorials by 1 each go. And instead of stopping like you would for a Maclaurin polynomial or a Taylor polynomial, you keep going. Okay, so if you know this, etc., you can always write down your Maclaurin polynomial. Okay, so how does that actually relate to our given function? Well, let's compute all the derivatives for our given function, and then we can write down our series, our Maclaurin series. Okay, so we've got e to the x. Now, what do we know about e to the x? When you differentiate it, you keep getting e to the x, okay? So for f of x equals e to the x, we have f of 0 equals e to the 0. Well, that's just 1. We know the derivative of e to the x is just e to the x. So what's the value of the derivative at 0? That's just e to the 0, which is just 1. And you can just continue this on, right? So the kth derivative, if you like, of e to the x is just e to the x, and so you can just continue this on. All right, so what does this mean for our function here? Well, let's replace that with 1, that with 1, that with 1, that with 1, etc. All right. So for our function e to the x, the Maclaurin series is 1 plus 1 times x plus 1 times x squared over 2 factorial plus 1 times x cubed over 3 factorial, and you just keep on going, yeah? All right, so you can see increasing the powers by 1, increasing the factorials by 1, and the coefficients are just positive 1. Okay, that was a pretty easy example, and in fact, in many Calculus 2 courses, you would be expected just to be able to write that down. Okay, so let's look at the second part of the question now, because this is where it gets a little bit more interesting. All right, so we've got a Maclaurin series. That we're told that it converges. In other words, for every x value, this and e to the x are one and the same functions. All right. Now that's important because it means we can do stuff with our Taylor, our Maclaurin polynomial. All right. Write down the Maclaurin series for this. So g of x is just x times e to the x. So let's take this series. Let's multiply it by x, and we'll get a series for x e to the x. Okay. All right. Now it converges for all x. Okay. All right. So let's use that, and we'll start a new page. So this is now the second part. I've got x e to the x equals x times all of this series here. Okay, so the dot, 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 of course, means we just keep on adding. All right, so if I expand this out, I'll get the following. Okay, that's x cubed. So this now is the series for the Maclaurin series for our G. Oh, Maclaurin. Okay, so we're pretty happy about that. All right, so just by using simple multiplication, we got a series for another related function. Now that's pretty cool. We saved quite a bit of time there because you wouldn't want to go back and compute all the derivatives for G. Okay, so we're on a roll now. Let's move on to the last part of the question. Differentiate to compute this series of constants here, positive constants, I guess, here. Right, so what we're going to do, we're going to take our expression for this, differentiate it, and then hopefully it will look a little bit like this. Okay, again, because we have the convergence, we can differentiate and integrate these sort of series, these infinite series. All right, so let's take this and differentiate both sides. So let's differentiate. To obtain, okay, so we're going to differentiate the left-hand side. We're going to differentiate the right-hand side. And then we'll see what happens. Now, again, I can do this because of the convergence. And I haven't said much about convergence formally. That's just one there. But I'll save that for other videos. Okay. See if I can squash that in, dot, dot, dot. Okay. So if I use the product rule to differentiate here, then I'll get the derivative of x times e to the x, which is just e to the x, plus the derivative of derivative of e to the x times x, which is just x times e to the x. So I get this. And on the right-hand side, I can differentiate term by term. So the derivative of x is just 1. The derivative of x squared over 1 factorial is 1, is just 2x. The derivative of this, the 3 will come to the front, of course. Decrease the power by 1, and you just continue on. You can see the pattern now, hopefully. Okay. Okay, I know what you're thinking. You're thinking, Chris, that's very pretty, but how does it actually help us calculate the value to the series that we're supposed to be calculating? Well, I'm glad you asked. Let me show you. What we would like to do is compare. You can see this and this are sort of the same if you plug in x equals 1. Okay, if I put in x equals 1 on the right-hand side, I get this series of constants. So let's plug in x equals 1 on both sides, because we've got equality. So I'll get an exact value over here, and I'll get the series over there. So let's put in x equals 1. So sub in x equals 1 to obtain. Okay, so on the left-hand side, I'm going to get 2e. Remember, e is just a special constant, which is about 2.7183. And on the right-hand side, I'm going to get this. Okay, I can continue that on. Okay, that's 3 factorial there. And lo and behold, if I write this in summation notation, it's exactly star. Okay. Now, just 0 factorial is interpreted as 1. All right, so the exact value of this series is 2e. That is pretty impressive from a series point of view, because it's tricky in a Calculus 2 course to come up with exact values for series. Okay, let's just quickly recap what we've done. We were asked to compute a Maclaurin series for this function. That depended on the value of f at 0 and all its derivatives. From that series, which we computed pretty easily, okay, there's the expression for the Maclaurin series. We wrote it down. We were told that it converged, and it converges for all x. Then we took our series and got a Maclaurin series for this function just by multiplying through. And then we differentiated, as was the hint, and we differentiated both sides and plugged in x equals 1 to obtain an exact value for a series. Now, I haven't talked about it much, but a lot of the underlying assumptions in those differentiations and multiplications of series involves the idea of convergence. I'll talk about that in other videos. This was just a simple one to get you started. Hope you enjoyed this video, everybody. Thanks a lot for watching, and I'll leave you with Colin Maclaurin. Bye, everybody. Bye.